My presentation today is going to deal with barrier liner technology. Could I have the next slide, please? The project is the AFRPL-sponsored Liner Barrier Technology Program, whose monitor is Burj Gashgarian. And the objective of this program is to advance the state-of-the-art for formulating liners with improved barrier properties to liquid migrants. Have the next slide, please. The presentation will cover three topics. The first of these will be barrier enhancing approaches. The second, polymer modification technique, and finally, permeability screening method. Next slide. The primary function of a liner in a solid rocket motor is to act as the bonding interface between the propellant and the insulation. Now, a secondary function, and probably just as important, is that it functions as a barrier to migration of plasticizers, curing agents, or any other items that can move back and forth between the propellant and the insulation. And that would preserve the integrity of the initial bond system that would be developed. Next slide, please. In the course of our work, we've uncovered a number of factors that affect the barrier properties of the liners that we were dealing with. First of these is polymer crosslink density. This is how tightly the polymer system in a liner is chemically cross-linked. The second deals with polarity differences between the migrant and the liner that we're using. Polymer density, this is the chemical density. This is actually the weight per unit volume of the polymer system that we're dealing with. Filler effects, and finally, polymer cohesive energy density. I didn't change that, by the way. Have the next slide, please. In looking at polymer crosslink density, we looked at a system that was selected because we could vary the crosslink density without chemically modifying the system to the point where it could influence the results. And what I'm showing here is a slide of the structures of the materials that we're using. A dimer acid, which is difunctional in carboxylic acid functionality, trimer acid, which is trifunctional in carboxylic acid functionality, and ERL 4221, which is the diapoxide that we use to link the whole system together. If I may have the next slide, please. We looked at a series of ratios of difunctional acid to trifunctional acid, which changes the crosslink density of the system. In this slide, you can see that the plot of permeability characteristics versus crosslink density, and the x-axis here is in terms of crosslinks per unit gram, shows that you can alter the crosslink density of a polymer system significantly, particularly with respect to dioctyl adipate, which was used in this instance, and not affect the permeability characteristics very much until you get to the very low end where the material is very slightly cross-linked. And it indicates that the permeability is not a linear function of crosslink density. The reason for this is not too clear. It may have something to do with a threshold molecular volume within the network that allows materials to migrate rapidly once a certain molecular size is reached when you remove the restraints of crosslink. Next slide, please. The next factor is the effect of polarity. In this particular slide, we're showing a medium, high, low polarity system, and then the slide you saw earlier where we looked at the low crosslink level of trimer and dimer, and then just trimer by itself, which would be the highest crosslink level. And we can see here that in a low polarity system, it doesn't make any difference on the permeability whether it's highly cross-linked or not. And when we deal with a high polarity system, we have high permeation through the system, And of course, in medium polarity, we have intermediate permeation through the system. So in this particular case, it's fairly straightforward. The ability of the migrant to associate with the polymer has a direct bearing on its ability to move through the polymer. Next slide, please. This is a difficult thing to demonstrate, but we chose this system because there is a similarity in structures between the two materials. In this instance, chlorine replaces a methyl group on a 1,2 polybutylene glycol type of polymer. The density of this system is about 40% higher than this. And as you can see, if we take a permeation of 1 for this, then this is 2.7 times, has 2.7 times the permeability. Now, some may argue that chlorine affects the polarity of the system. We feel that this system is about the same polarity. They're about the same polarity, so that we do not feel that the polarity effects were there. If, of course, this were a more polar system, we would expect a higher permeation. So what it implies is that we have filled the void area with more material. There's more weight per unit volume in the polymer. Consequently, it restricts the ability of materials to intersperse themselves through that polymer network, thereby reducing the permeability. Next slide, please. We looked at the effect of several fillers on their ability to retard migration through the polymer network. The system we chose here was the B2000 system. That's the 1,2 polybutylene glycol. And the reason we chose that is it's an intermediate polarity material, and it has a fairly good permeability to most things. Consequently, the effect of any filler would be enhanced in the presence of this particular matrix, and we would be able to see the effect, and it would not be overshadowed by any of the any polymer characteristics that might retard migration. Taking the no filler situation as one, we see an interesting thing here. As soon as we add silica to the system, the permeability factor goes up by 2.5 times approximately. As we increase the silica content, it comes down, and finally at 50% silica, the permeation is below that of no filler at all. We go to wollastonite, which is a replacement material for asbestos. It's a small fiber material, principally calcium silicate. And in this instance, we immediately retard the permeability of the migrant through that matrix at the same level where the permeability was increased by silica. So this turns out to be a very effective filler. Now here we see a polyimide filler, which is an organic filler. It tends to reduce it better than silica. And then we look at polystyrene, which even at the high level, the permeability is greater than no filler at all. So the message here is that fillers can both increase and decrease permeation rates of migrants through liners. Now the reason for this is not exactly known. We think that the ability of the migrant to be attracted to the surface of the filler plays a role in, particularly in the case of silica, in enhancing that permeation rate. However, as the silica content increases, the amount of binder decreases, and the matrix through which permeation takes place decreases proportionally. Thereby, we get a reduction in permeation. Next slide, please. We wanted to see what the effect of isomeric structures were on permeability, and we chose these two systems. They have about the same polarity characteristics. The main difference between the two is that there is an ethyl side chain in the B2000 matrix, and there is no side chain in the 1,4 polybutylene glycol system. Now, what you see with these two is in the 1,4 system, the first one here, there's close association by the chains, and as a consequence, the material in its pre-polymer state is a relatively high melting material. It melts somewhere around 50, 60 degrees centigrade. By contrast, this material is a nice liquid, low viscosity liquid at room temperature, because this ethyl side chain prevents close approach of the backbone chain. It cannot crystallize readily. So in this, we cross-link the systems to the same cross-link density, try to keep everything constant, and we measure the relative permeabilities, and we find that this material has a permeability coefficient something around 3.5 times greater than this one over here. So we have to deduce that there is a definite effect of the structure of material and not just the polarity effect. So these are isomers that show differences. Now, there are other materials that we have used in the system that show very little difference. So it has a bearing on what you're migrating through the system as well. But in this particular instance, using dioctyl adipate, which is a widely used material, we can see quite a large difference. Can I see the next slide, please? Now, what I've tried to do here is summarize the pros and cons of the different methods that we have looked at. Cross-link density, it's generally applicable as a barrier. It's an easily attained material. Has some problems. The liner material itself is high modulus. It oftentimes gives you bonding difficulties. The glass transition is usually high, which means that it's not readily used at low temperatures for tactical applications. And generally, because the peel values in a system are related to the elongation modulus characteristics of the liner, we generally see low peel values. Going after polarity differences, it's good when you have an extreme system where you can use a nonpolar liner and a migrant that is highly polar. An example might be a nitrato-plasticizer against a butadiene-based liner. You do not have to have a high cross-link density in this instance, simply because that is not what's moderating the migration of the material, and thereby you can easily adjust the modulus. However, polar liners are not moisture resistant. Moisture tends to penetrate them readily, and if the system is subject to degradation by moisture, that is not a desirable situation to have. And they're not generally useful because most of the systems that we deal with are kind of intermediate in polarity and we can't contrast them well, although some of the new energetic systems we're dealing with do have the potential for designing this kind of a system. Polymer density, it's applicable where you have intermediate polarity differences. We can slow things down simply by increasing the density of the polymer. You do not require a high cross-link density, which means you can control the modulus much better. However, well, and it's more generally useful than polarity differences. However, you still require a polarity difference somewhat. And the selection is limited because there are not a whole host of materials out there that would satisfy this kind of a requirement that we can use in this business. The filler generally improves the barrier characteristics. High cross-link density not required, and you can adjust the viscosity with the fillers that you use. However, some fillers increase migration, as we showed earlier. It can raise the liner modulus, which it usually does. And there is the problem of particle settling. So it has to be formulated such that you don't get striations and separations of particle sizes. And finally, polymer self-association, which relates to the isomeric structural differences. High cross-link is not required, and it's applicable to polar migrants. However, it's limited to polar liners. It takes polar materials to self-associate a lot. It generally will produce high pre-polymer viscosities, which makes handling and fabrication a little more difficult. Association can be broken by strongly polar migrants, which would preferentially solvate them and swell the chain. And generally, these materials do give you high glass transition temperatures. Next slide, please. Now, in this particular program, although we were concerned with barrier properties of liners, the applicability was to the tactical environment, specifically in concentric grain design, where we would actually put a liner between two grains. And the requirement for a material like that is that the liner have a modulus at minus 65 degrees Fahrenheit comparable to that of the propellants that it lies between, or sandwiched between. So in going through the literature, we came up with a process called graft copolymerization. And what I am showing you here schematically, and that's not the way we spell schematic, is the way we went about doing it. We co-react a difunctional acid with a difunctional epoxide to produce an intermediate molecular weight polyester that has pendant hydroxyl groups, functional groups. Now what we do next is that gives us one kind of prepolymer. It generally has a glass transition temperature that's too high for tactical use. But the next thing we do is we take another material and we graft it into each of these hydroxyl groups via the OH and the isocyanate reaction. And this material has a low glass transition temperature, but it's generally highly permeable and not suited in a lot of respects to good bonding. Now the reason we chose this material up here because of this is the dimer acid type of situation. We found that the presence of pendant functional groups, or non-functional groups, I'm sorry, allow us to get good bonding when we have a very tightly cross-linked matrix. Normally, if you have a tightly cross-linked matrix with no groups sticking out available to interact with the prepolymer of the propellant, you can't get good bonding. So with this system, we're able to go to high cross-link densities and still get good bonding. So we chose to make the prepolymer with that. Now, as I said, that has a high glass transition temperature. By combining in another material, grafting it in this fashion, we come up with a fairly highly cross-linked liner that has some rather unusual properties. I have the next slide, please. Small changes in the polymer that has the low glass transition temperature produce very large changes in modulus of the liner at -65. We looked at LD-164, which is the 1,4-polybutylene glycol, and R45 in this instance, which is the HTPB system. And both of these materials exhibit low glass transition temperatures. So we were able then to make liners with moduli in the region of that of the propellant systems themselves at -65. Could I have the next slide, please? To illustrate what we were able to do here, polymer A is the dimer acid diapoxide prepolymer. Combining it with polymer B, in this case LD-164, at 60 equivalents, we were able to achieve a modulus of 3,600 at -65. Going with R45, a modulus of about 3,200. And we look at B2000, which gives us a good high elongation at -65, but a modulus of 111,000. And R45, the HTPB polymer, has good low glass transition temperature properties. And we can get a low modulus liner, again, using that material by itself. And Trimer illustrates a high modulus. Now this is a material that gives good barrier properties. This material gives poor barrier properties. This illustrates the fact that the highly cross-linked systems give us high moduli at low temperature, and the materials that are easily permeable, low modulus. So we wanted to combine these properties. We obviously have to form a compromise here of sorts, and that's exactly what we did. Have the next slide, please. I'm sorry, wait a minute. Okay, let me stay back with the other slide. Go back to the other slide. If you could remember back at the other slide where we varied the amounts of the low TG material we added, we're probably, in this case, we're just at the bottom of that curve. So we're on a fairly shallow portion of the curve. If we back off on equivalence here, we can move up that curve. We still get good elongation properties, but the modulus climbs. The thing that, oh, I'm sorry, I do have it here. I thought I had it on another slide. The relative permeability of these materials goes along with what I was saying here. We were able to effectively reduce the permeability and yet match the modulus properties of the R45 system at -65. R45 has a relative permeability of 1.5, the B2000 at 1, and these were about 1/3 that of the R45. So what we had achieved, in essence, was a material that could replace R45 as a flexible binder for -65, but has about 1/3 the permeability characteristics that polymer has. So it looks like it's a useful technique for tailoring the physical properties or mechanical properties of liners to be relatively constant over a wide temperature range. Next slide, please. Now, you've seen a lot of relative permeability columns up here. The technique that we chose to to use to evaluate materials as far as permeability went. It's called a swelling ratio technique. And the way we do that is we cut a strip of the liner material, we put it in the migrant of choice, and we follow the change in length of that material with time. We assume that the change is isotropic, that the material expands in all directions at an equal rate, and simply then ratio the cube of the length of the material relative to what it was initially, and we come up with a swelling ratio. Could I have the next slide, please? This is typical of the kind of curve that we get. Now, we found that if we take the initial slope, tangent, to that curve, that we come up with a value that is directly proportional to the actual permeability coefficient for that liner for the given migrant that we're looking at. And this distance here, incidentally, is somewhat proportional to the solubility characteristics of that particular liner. Can I have the next slide? Now, last year I gave a presentation in which I discussed a technique that we had developed on the liner technology program, also AFRPL sponsored, in which we had a technique for measuring permeability of various migrants, liquids particularly, to the liners that we were concerned with, and we called that a diffusometer. I'm not showing that here since I showed it last year, but the technique allows us to actually measure the permeability coefficients of the liners for any material that might migrate through it. And we do this in a simple fashion. We come up with the permeability constants. These don't show up too well, but these are the permeability constants, and they follow the Arrhenius relationship for activation energy, which allows us to measure these constants at least, say, 3 different temperatures and plot them against each other and extrapolate to room temperature. Generally, the permeability of liners to most of the migrants are real slow, real low at room temperature, and it's a very difficult